lecture of Chapter 4. Today we are going to talk all about the periodic table. The periodic table is one of the most important resources for a chemist. There's a ton of information contained on this periodic table. We can figure out how many protons, neutrons, and electrons something has. We can figure out how it's going to react. We can tell about an element's properties. There's all kinds of information on this periodic table, and one of the goals of taking a chemistry class in college is to figure out how to read this periodic table. It's, as soon as you figure out how you can see the information on it, you will never need another cheat sheet because everything is on this periodic table. So it's pretty cool. So on the periodic table, obviously there are elements, and elements are pure substances from which everything else is built. Everything in the entire world is built from elements. We say that these atoms, right, are the building blocks of matter, and each one of these atoms is a different element. And over the centuries, elements have been named for famous people, geographic locations, mythological figures, minerals, planets, right? We've got, like iodine is named for a Greek god. We've got titanium from the Titans from mythology. Uranium is for the planet Uranus, right? We have all of these different names, right? And whoever comes up with this element, right, whoever discovers the element gets to name it, which is pretty cool. So like we've been doing, right, our elements are all represented by chemical symbols, and you guys have had to learn them, like, hydrogen is represented by the letter H. And so we've been working on memorizing those in this course. And chemical symbols are always 1 or 2 letter abbreviations for an element's name. When the chemical symbols contain 2 letters, the second letter is not capitalized. So like if we look at cobalt, cobalt is CO, right? But that's capital C, lowercase o. If we write capital C, capital O, that means there are 2 different elements present. That's carbon and oxygen. So every time you see a capital letter, that's telling you that it's a new element. So make sure that you're paying attention to the capitalization. It matters. So here's a couple. We've learned aluminum, right? Al. Silver we'll get to Ag. Gold is Au. Sulfur is S, right? But if you look at all of these, the first letter is capitalized, the second letter is not, if there's a second letter. There's not always a second letter. Okay, go ahead and find your Chapter 4 lecture worksheet and do problems 1 and 2. That's just selecting the correct symbol for each element. Okay. Now, no talk about the periodic table would be complete without talking about Dmitri Mendeleev. He is known as the father of the modern periodic table, and he essentially gets credit for organizing the periodic table as it looks today. He was not the first person to organize the elements. There was a lot of work done prior, kind of grouping them by 3. We saw there was a repeating pattern every 3 elements that had been discovered. And so that was called the law of triads. There was also this repeating pattern that people noticed called the law of octaves. And that happened every 8 elements. So there were a lot of work done organizing the elements before Dmitri Mendeleev, but it was more like, hey, these 3 elements kind of react together. Let's put them in a group. Just kind of, put them over here in a cluster of 3. And these ones all react to, kind of similarly. Let's put them over here in this cluster of 3. And there wasn't a lot of work being done to show more than just, hey, these react together. And so Dmitri Mendeleev was like, let's take all of these different ideas and combine them into one periodic table. And what he noticed was that if you lined up all of the elements by increasing mass, so hydrogen has the smallest mass, and then helium has, a greater mass, and then lithium has a greater mass. So if I put them in order of increasing mass, then he started to notice that there was a pattern that repeated every once in a while, right? Like lithium behaves really similarly to sodium. They both react when you put them in water, and so does potassium. And this was happening every 8 elements. And he was like, hey, there's this pattern, right? And beryllium kind of reacted like magnesium, which reacted like calcium, right? And helium reacted like neon, which reacted like argon, right? And he started seeing this repeating pattern if he put them in order of increasing mass. So he said, okay, well, instead of just putting them in this big long line, why don't we stack them up so that they're still going in order of increasing mass going this way, right? So this is still increasing mass, but up and down, they have the same properties. So he said, okay, everything that reacts the same, we're going to put in a column, and then we're going to keep these lines, though, with the increasing mass. So he put them in a table. So all of them in a column have the similar properties. So these, we'll learn later, these are all alkali metals. These are all alkaline earth metals. These ones I circled over here in the green, those are noble gases, and these are all halogens. And so this was really revolutionary. So now he's displaying two different pieces of information. From left to right, he was organizing it by increasing mass, and going up and down, he organized it by similar properties. So that was really cool. But what he did that was really revolutionary is he took all of the elements that were known at this time. So you can see them kind of in color in the back. All of the elements that were known at this time, he put them in order of increasing mass going left to right, just like we were talking about. And he put them in order of similar properties going up and down, just like we were talking about. But the thing that was really revolutionary is that he left holes in his periodic table. There were gaps. This was crazy, right? This was like super revolutionary. And because he said like, okay, if we go in order of increasing mass going this way, right? I could put titanium in that box, but in the next row, going this way, if I'm organizing them by increasing mass, there's this yttrium that falls in between, this one with a Y. And then zirconium. And titanium reacts like zirconium, so I know titanium has to go here and not here. So titanium's got to go over zirconium. So there must be something that goes in this box that has a mass between calcium and titanium, but that behaves like yttrium. So I'm just going to leave a space there because something's going to go there. Just because we haven't discovered it yet doesn't mean that it doesn't exist. So he left these spaces in the periodic table because he said there's an element out there that goes in this spot. We just haven't found it yet. So I'm going to leave this space on this periodic table so that when we do find it, because we will put it in this place. That was really revolutionary. And what was cool is that he was right? He organized it in order of increasing atomic mass. He left the spaces where unknown elements that fit. And later, actually, and I'll come back to this slide, later we actually discovered these elements. He found scandium, gallium, and germanium. And the properties that he predicted, because he said, okay, it's going to behave like yttrium. It's going to have a mass between calcium and titanium, right? And he was right. They were really, really, really close. His predictions for these properties were super close. And the same with gallium over here and germanium, right? He knew the masses pretty accurately. He knew how they were going to behave because gallium was going to behave like aluminum and germanium was going to behave like silicon. And since he was so close and he was like, it was really, close to being the right values, his table was accepted. People are like, wow, that was impressive. You must be right. And he actually, going back to the slide previously, said that if an atomic weight of an element caused it to be placed in the wrong group, like if the mass was going to cause it to be in the wrong group, then whoever did that weight, they're wrong, not him, right? He's like, if the mass of the element is going to cause it to be placed in the wrong group, then whoever came up with that mass is wrong. The mass is wrong, not me. It's got to be that the mass is wrong. And so he actually went through and corrected the masses of beryllium, indium, and uranium, which was crazy, right? And so people are like, okay, he can predict the properties of elements. He can correct the masses of elements. This table must be right. This must be how the periodic table is supposed to be arranged. Like there's no other way that it could ever be done because he is so right, which was cool. And so he's known as the father of the modern periodic table because of these spaces, because of his ability to predict what's going to go in those spaces, which is really, really neat. However, even though he was able to, correct these masses and he was able to predict the properties of the elements, we started to get more and more accurate atomic masses. And when we started to get more accurate atomic masses, we started noticing some problems. So if you can find your periodic table, go ahead and pause here. Find one that has masses on it, okay? And then I want you to look at these elements. I want you to look at argon versus potassium, right? And cobalt versus nickel and these other ones. And I want you to see, right, because it's supposed to go from left to right in order of increasing mass. So these ones should have a greater mass. And I want you to look at them on the periodic table. Okay, so now if we go and we look at argon versus potassium, right? Potassium, because it's in the fourth row, it's not in the third row like argon is, right? Argon's here. And then, if we were going from left to right, then argon should have a smaller mass than potassium because potassium is in that next row. But if we look at the mass of argon is 39.948, and the mass of potassium is the mass of 39.098. So argon has a higher mass than potassium, but I just told you that this is arranged in order of increasing atomic mass. So argon should have a smaller mass of potassium according to Mendeleev. And if we look at cobalt versus nickel, right? Cobalt has a mass of 58.933 and nickel has a mass of 58.693. So again, they should be switched, but they can't be switched because cobalt behaves like all of these other ones and nickel behaves like all of these other ones. So we can't just switch them because they're supposed to be in that column. So people were like, man, Mendeleev was onto something. We thought it was really, really great, but now he's wrong. It's not in order of increasing mass. So now what? Well, this guy, Henry Moseley, came along and he's like, not to fear, I have the answer, right? He worked with X-rays. And what we could do with X-rays is we could determine the actual nuclear charge. And the nuclear charge really will just end up being the number of protons because that's the stuff that's charged in the nucleus. This will also end up being the atomic number. He was able to figure out the number of protons in each of the elements, and he said, okay, this periodic table is not arranged by the atomic mass, it's actually arranged by the number of protons. So you don't have to change anything. The only thing we have to change is the way we say that it's organized. We don't even have to change the organization. We just have to say how, that it's not organized by mass, it's organized by the number of protons in the element, and that will be the atomic number. So if you look at these numbers at the top, those are the number of protons. Those are the atomic numbers. And so this periodic table is not arranged by mass, not anymore. It's arranged by the atomic number. So this is a common question that I ask on tests. I ask, how is the modern periodic table arranged? And a lot of people will say it's based on atomic mass because that's how Henry Mendeleev organized it. By Dmitri Mendeleev organized it, but Henry Moseley fixed it, and it is now arranged by increasing atomic number, okay, or the number of protons. So make sure you make a special note of that in your notes, that it's not arranged by mass anymore, it's arranged by increasing atomic number. So what's really interesting, and just kind of I think it's interesting, if you'll look at the dates that he was alive here, and that's not a very wide range, right? He wasn't alive very long, which is unfortunate. And you'll see here, he's actually very young in this photo. And so thinking about your knowledge of history, what was happening around 1915? So the thing that was happening was World War I. his research, right, he was a great researcher, great chemist, kind of worked in Chem, right, physical chemistry. His research was actually halted when the British government sent him to serve as a foot soldier in World War I, right? And you can think, if you think about what you know about scientists, of course they're going to make great soldiers, right, But so they sent him off to the front lines, and he was killed by the age of 28. So all of this discoveries that he was doing with his work with X-rays was before 28, which is crazy. He was on to make, to do great things, and instead of, continuing his work in science, the British government was like, everybody's got to go to war, and so they sent him off. And so now, if you look at this last point, because of this, the British government later restricted its scientists to non-combat duties during World War II. It's like, all right, we can't afford to lose any more scientists. Besides they clearly don't seem to be very good in battle. Let's just keep them in the lab where they belong. All right, a little more about the periodic table. So when we talk about the periodic table, going from left to right, we call these periods. These horizontal rows are called periods. And so what I would do as we're going through this section, I would print yourself off a blank periodic table. And I actually have one on Canvas for you. You can go and you can find the periodic table. That's the one that I give you on quizzes and tests. And I would print that off and start making notes on it. So make yourself a note that the rows are called periods. And the columns going up and down, those are called groups. And sometimes you'll hear them called families as well. But remember that the elements in a group have similar physical and chemical properties. So if any elements fall in the same group, right, in the same column, they're going to behave similarly. So if we look at the periodic table, we have two different ways to talk about the group numbers, okay? We have the letter A that can represent the elements 1A to 8A and these main group elements. So those are up here. So we have 1A, 2A, 3A, 4A, 5A, 6A, 7A, and then this would be 8A. I don't know why it says 0. And these are in Roman numerals. You'll also see them written as like 8A and 7A, etc. Okay, and so these groups here, these are called main group elements. Okay, and then if you'll look, I know it's kind of faint, but the ones in here, these are numbered by B's. And these are called transition metals in the middle. Okay, so these are transition metals, the ones in the middle, and the ones that are off on the sides like this, these are called main group elements. Okay, so again, I would print yourself off periodic table and make all of these notes on it. You can pause here if you haven't done so already, and then come back once you're ready. So, one way to number them is the 1A through 8A for the main group elements, and then there's this B lettering that happens for the transition elements, but it doesn't go in order. It's not like 1B starts on the left and 2B, 3B. It's got kind of a weird numbering system. So instead, a lot of times we will just use the numbers 1 through 18 to go from left to right, which is a little bit easier. So instead, we'll do 1, 2, 3, 4, 5, 6, 7, etc. And then this one would be 18. Okay, so two different ways to number them. Oftentimes we'll use just the 1 through 18 because then it actually goes in order. Some of the groups have names. So group 1A are called the alkali metals. Group 2A are called the alkaline earth metals. 3A through 6A don't really have names. We just kind of call them, we'll say like, oh, aluminum's group or carbon's group, right? We'll name them based on the first element in the group. They don't really have other names though. And then group 7A are called the halogens, and group 8A are called the noble gases. And I'm going to write these on the next slide. But the ones that you need to know where the alkali metals are, the alkaline earth metals, the halogens, and the noble gases. Okay, so I'm going to write these like I said here. So this is group 1A, and these guys are the alkali metals. these guys in group 2A, these are the alkaline earth metals. I also want you to know these ones in the middle, like I said earlier, these are called transition metals. So I do want you to know these as well. And then the group 7A right here, these are called the halogens. And then group 8A, this last column, these are the noble gases, and we will talk a lot about them. Okay, so these are the groups that I want you to know. So alkali metals, alkaline earth, halogens, noble gases, and the transition metals. And then remember, periods are these guys, right? These are all the periods, and they are numbered, 1, 2, 3, 4, 5, 6, 7. And then the groups are the ones that go up and down. And again, the groups are the ones based on similar properties. Left to right will be on increasing atomic number, not atomic mass. Okay, so periodic law. All of this summed up in periodic law. When the elements are arranged in order of increasing atomic number, again, not mass, there is a periodic pattern in their physical and chemical properties. So that's saying that if we, put them in order left to right and then line them up, we can notice these patterns going up and down. So if you go to Canvas, I'm not going to play this right now, but if you go to Canvas, there are 2 different videos on alkali metals that demonstrate the reactivities of that element. And so you'll see the alkali metals, they all react with water, which is really cool. There's some of my, I wrote it twice. There's some of my favorite elements, just because you can stick this, they're like little soft metals, and you put them in water and they explode, which is cool. And as you go down the periodic table, they get more and more reactive. So, if you're looking at the periodic table, one of the first ones they do lithium, right? And lithium makes kind of a little bit, it reacts, but not super great. So lithium, but then as you go down and you find sodium, sodium reacts even more. And then potassium gets bigger, and rubidium and, cesium, they start to get bigger and bigger and bigger reactions as you go down the periodic table. And we'll talk about why that is in later classes. But the key part here is that they all have a similar property. They all react when you put them in water. Whereas other metals, like if you think about a piece of maybe aluminum, right? If you put aluminum in water, like a soda can, it doesn't blow up, but all of these metals do. And this is to demonstrate that elements in a given group have similar properties. Okay, so check it out. It's actually really entertaining. Okay, so this is a periodic table, and it's got the ones labeled on here that I want you to know: alkali metals, alkaline earth, transition metals, halogens, and the noble gases. Okay, and so those are all labeled on there. There's this zigzag line here that it's talking about, and this is so you can find these green elements that are called the metalloids. So we're looking at this periodic table. We have the metals are in blue, the metalloids are in green, and the nonmetals are in yellow. And I would actually recommend on this periodic table that I told you to print off, that you've been making notes on, I would actually go through and color the metals, the nonmetals, and the metalloids. And this can be a really good resource as we move forward, especially when we do bonding, or if you have a color printer, you can just print out the slide. That will be really helpful. But otherwise, if you don't have a color printer, I would color in the metals, nonmetals, and metalloids on your periodic table, because it will be really, really helpful in later classes when we start doing bonding and we need to figure out which ones are metals and which ones are nonmetals. But the metals are always on the left of the periodic table, the nonmetals are on the right, and they're all separated by these metalloids that border the zigzag line. If you do choose to color this, make sure, I'm going to point this one out, hydrogen is a nonmetal, okay? It is in yellow, so make sure not to color it in blue or whatever color you choose to make the metals. It is a nonmetal. Okay, once you've done that, go ahead and complete lecture worksheet problems numbers 3 through 6. This is just getting you used to figuring out whether something's a metal, a nonmetal, or a metalloid. Okay, so we have these different types of elements, and right, the metals, nonmetals, and metalloids, and they all have different properties. And most of the metals are shiny solids. And you would, if you think about a metal, then that would make sense to you, I think. Most metals are shiny solids, and we're familiar with things like copper, gold, silver. They have other properties as well, though. They are ductile, which means that they can be shaped into wires. That's why we use things like copper for the wiring in your house. They are malleable, means they can be hammered into sheets, like if you were going to put on a tin roof or something like that. They are good conductors of electricity, again, copper wires, right? They are also good conductors of heat. And if you think about like the seatbelt in your car, right? It's often over 100 degrees in the valley, and if you get in your car and you touch that seatbelt in the summertime, that is hot. Metals are really good conductors of heat. Metals are melted at much higher temperatures than nonmetals, right? It would take a lot of heat to melt a metal. And they're solids at room temperature, except for one of them, and that one is mercury. Mercury is a liquid at room temperature. It's pretty metal. It's super shiny and silver. It's gorgeous, but also really toxic, so we don't keep it around. Nonmetals are pretty much the opposite. So what I would do is go through and memorize all of the properties of the metals, and then know that the nonmetals are completely the opposite. They are not shiny, they are not malleable, they are not ductile, they're really poor conductors of heat and electricity, and they typically have really low melting points and low densities. And what we mean by low melting points is they melt at low temperatures. And for this reason, most of them are gases at room temperature. A lot of them are. Some of them are also, or one of them is a liquid, and very few of them are solids. But if they're a solid, then they melt at a really low temperature, whereas the metals melt at really high temperatures. This is sulfur here, and I just point this out because we live near Hanford. So if you've ever been been to Hanford and you've had some of the water there and it tastes a little bit wonky, right, or it smells a little bit wonky, it's because there's sulfur in the soil in Hanford. And so that's what's causing that. So if you just have pure sulfur there, though, it's this yellow powder, which is neat. And then the metalloids, so all of the elements except for aluminum that are along that zigzag line, right? So we'll go back and look at the zigzag line real quick. So here's the zigzag. So all of the elements that touch this zigzag line, except for aluminum, aluminum's a metal, but all of the other ones are metalloids. And so metalloids are elements that have properties that are kind of similar to the metals, but kind of similar to the nonmetals. They fall in between. Okay, they are better conductors of heat and electricity than nonmetals, but they're not as good as metals. And they're called semiconductors, which means they kind of conduct heat, they kind of conduct electricity, right? Not as well as the metals, but better than the nonmetals. And for this reason, actually, we use them a lot in electronics. So one of the metalloids is silicon. And if you think about, the Bay Area, you know that near there is Silicon Valley, and they're known for electronics. And the reason it's called Silicon Valley is because they use silicon in a lot of their electronics because it is a semiconductor. It has properties that we can modify and we can vary based on temperature and pressure to, change how well it conducts electricity, which is really, really useful in electronics. So that's why it's called Silicon Valley, because of all the use of technology and because of the use of these metalloids. So here are an example of a metal, nonmetal, and a metalloid. So this will sum up some of the characteristics. So like, see the metal, it's shiny, whereas, the nonmetal is dull. And, the metal we can draw into wires, right? It's ductile, but the nonmetal is brittle. So if you try and, draw it into a wire, it's just going to break. Same kind of thing, you can hammer metals into sheets, but if you hammer a non-metal, then it's just going to shatter. So this will kind of sum up all of the properties of the metals, nonmetals, and metalloids. And you'll notice that the metalloids fall in between the the metals and the nonmetals. Sometimes it behaves like a metal, sometimes it behaves like a nonmetal. Okay, go ahead and find your lecture worksheet again and complete problems 7 and 8. And this is actually the end of this set of slides. It's not the end of this particular lecture because we're going to go on and we're going to talk more about the periodic table, but it is the end of this set of slides to give yourself a break so that you can, walk around, get some water, collect your thoughts, and then come back. So I'll see you next time for Chapter 4, Part 2.